Hello, everybody. I'm Professor Nicolin Govender. My talk for today will be looking at how do we take advances towards digital twins for milling automation, and as well as how do we get to a place of virtual plants, and how can simulation, while we are building this virtual environment, be used to give you new insight into mining processes. So just a quick forward, when you pick up the digital version of the slides, you can read through this. So this is it again, Professor Rajamani, who started the Communication Center at Utah, uh, passed away last year. So a lot of the work that's done here has come from his work. So this is just a little bit in memory of him. Okay, so I'm going to be covering quite a bit. So in case I forget what's talking about, you'll see the slides are color-coded on the top. What I'll be introducing here is granular material, what it is. We'll then be going on to the overview of models using comminution, the existing models and tools, an overview of what do we mean by physics-based simulation. So that's using the street element method. What are the challenges in getting a digital twin? How can GPU technology be used to accelerate things? What insights we can get when we have a tool that has proper physics in it and GPU acceleration. And finally, we look at some digital twin examples from our partners, ACN Automation, various other people working on things. So the first thing, what is granular material? So when you look at a mine, well, from the mill to the mine, the entire problem is granular material. And one of the challenges, we do not know why it behaves the way it does. There's no complete theories that can fully predict the motion of the material, unlike a fluid or gas, where there are mathematical equations for the transport. This doesn't exist for granular material. It exhibits behavior that's typical of liquids, solids, and gases at various stages. And mining, well, mining is a granular material problem. Now you will see it's the entire challenge of what we're trying to do. We want to liberate minerals from the rocks. And my entire talk will look at how we can use computational tools to do this more efficiently. Now you can see granular material here. It will flow from a hopper and then it will jump. And then you have to do all sorts of techniques to get it to flow again. If we treat it as a fluid, and here you see a very large coal silo that broke and collapsed because of the stresses induced. So the material is very complex. So we treat it as a fluid, nope. And then we say, okay, we treat it as a solid. And here you can see landslides where the earth gave away. So, okay, it behaves as a solid. And at some point, it can then transition to a fluid. So the material might seem simple, rocks in a pile, in a heap. But once we start moving it to the various processes, it exhibits complex behavior depending on the environment it is. So to understand mining comminution, you need to understand granular material. And what's the challenges? Well, industry is in 4.0, and mining, I still say we're stuck in 2.0. Well, every process of liberating minerals from ores involves granular material. And as we said, very, very complex behavior to vast ranges of sizes and shapes. And you will see later on as we speak, what's the key thing about shape. Because everything we do, sieve sizes, everything else assumes these are spherical. And I've never seen a spherical rock. Okay? And because of this complex behavior between the shape and the size, every batch of material has a slightly different behavior. And well, what that leads to is here, that over-engineering. So here we're trying to inflate a tractor tire with a bicycle pump. It's the wrong tool for the job. Here we have a hopper that's jammed and you keep taking a hammer and trying to break that. Well, in a plant, if you want to become automated or you want to have as less intervention as possible, you cannot deal with issues when it happens. You want to pre-guess this. And if there has a case where this does happen, you want to be able to say, can I quickly get an answer from a simulation? So molds are very, very harsh. We can't go inside them. Well, we can go when they're turned off. But once the motion starts and we want to see what's going on, it's very, very difficult. And always joke, if you want to use trial and error, well, bad things happen. So a mill, with the cost of breaking the machinery or the challenges that come with safety, you cannot go and test new things in milling. Hence, progress is very, very incremental. But you will see when we have a simulated environment, then you can go and test these things out. So current models, well, one thing that doesn't get much attention is the journey from the mine. And as you can see, all extraction still lags behind. We're still sitting in the 1800s trying to break things with a pickaxe. Well, we have dynamite, we blast, and we get things. But the shape and the size, what we call the morphology of the ore, has a huge impact on what goes on from the crusher to the end. And if we paid more attention to this, uh, we can get much more detailed information, and we can actually save ourselves a lot of the effort in the liberation process by understanding what's the optimal size and shape of this, how do I best get it from blasting. So while there are macroscopic models of this that give us this information, it's not based on fundamental physics to get size and shape fragments. So using discrete element, that we will see what it is about, finite element to a degree, where you can represent the physical of this, you can optimize these processes very, very well. When it comes to the actual milling, the comminution, well, there's a lot of mathematical models that have been used, as well as historical data. Everyone knows these, the Hogg first two models coming out from Utah. Initials Powell single ball models again, and where you looked at the path of material. And when the material is very well behaved, stays in that position, is fairly okay. It assumes that particles don't really move, these regions stay static. And you can basically identify a charge profile by something like this equation. And you will see when we look at the simulations and actually look at reality, this is not entirely the case. For certain things like ball milling, once you start to cascade, once you start to cataract and your chart starts getting thrown over, these assumptions don't fully hold. And there are various other tools that you would use now. So Mollycop tools, various other methods. And some of the fundamentals here where you looked at, again, is saying that we know that we can actually scale down. We can in fact stand in a lab and then scale up again. And that's the one thing that makes applying physics simulations to milling quite nice. So the current state of the art is this, using historical data, using statistics and population balanced. And what's the limitations of data-only models? Well, when it comes to sag and angles, the material is not uniform. This usefulness diminishes. The moment I deviate from the average, we run into trouble. And here's an example, it's a joke, where a statistician crossed a river which was on average 1 meter deep and he drowned. So when we start saying on average, we miss a lot of information that can be critical to optimization and production. So when we came to the 90s, Rajamani and Misra introduced using discrete element method, so simulating each particle, be it ore or ball, and optimizing relief angles. So we went from doing everything 90 degrees to understanding how relief angles work and building on that. So I look at this here and you say, often we get promised this nice image on the left, and when you actually get something, it's what we see on the right. So what we see and what you get is completely different. So there's been a huge trend recently on AI and data science. Well, it's not magic. Yeah, you're not exactly going to get that. And the reason for this is the information, the sensor information from this and historical data is limited to the macro scale. It's not on the particle level scale. So yes, it is useful and helpful, but we can do better. And in the talk today, the rest of this will show you how can we do better by using physics simulations. Because currently what we deal with is this. You have your input, black box, output, and we're the observer. So we only observe two things. And what we say now is, can we look inside this black box using physics simulations, combining it to give us digital twins? with both data science, AI, and plant methods. So we call it going virtual. The idea of the whole plan is that I have a virtualized plant. I can pick any device in there. I can then have a representation of current. I can then get a physics one. I can use augmented reality, as you see on the right, to train engineers, to train people, to mill operators, to understand these things. So currently, simulation has been used for a number of years, but it's been done in individual units. And the process from the mine to the mill consists of various different units. And while we have simulated them individually, you may already have such simulations or seen things or have tools for them. When you want to connect everything up to tell me what's going to be an ultimate throughput based on changing something, it becomes not so clear to connect these things up. So we cannot answer these future questions for upstream or downstream. And that's what a digital twin, going virtual, in my understanding, needs to be. It can ask what's going to happen in this case, and we get an answer from that. Okay? So what is the challenge? What is the fundamental challenge that we have here? Well, this appropriate type of model needs to be chosen for each unit. So be it physics-based, be it data, be it whatever analysis. And we need to see what fidelity that we need. So the calibration, choice of simulation parameters, this is a challenge for people working in industry. So these things need to be highly automated. You want to have this digital representation of a different size of rocks based on their hardness, shape, different designs of conveyor belts, tubes, mills, different operations, all available to you. That's what we mean creating a digital twin. So the remainder of this talk will be using one particular example of this, the discrete element method, as a tool to train AI-based models, machine learning models, but also give us new insight into this particular process. So as we said, observation-based approaches focus on what we want to do here is we want to illuminate the black box. We want to know why something works rather than what works. And that is very important. It's a scientific way of understanding something. And physics-based simulations using DEM, we explicitly track the motion of each particle in the mill. So we have microscale information on breakage, sharp profile, and wear. Simulation gives you insight that you just cannot get from literature. And because it's specific to your operation, you can optimize it. So digital twins are at the heart of Industry 4.0, and the challenge here is to use the combination of simulation and plant data. And while DEM simulations have been used for milling over the years, oversimplification and long run times make it unfeasible. So what we need to do is find a combination of these. And we will look at some of the challenges in addressing this. In English, there's a saying, there's no free breakfast. Yeah, and we will see why that, yes, we have a better solution, but there's always a challenge. However, that challenge can be solved with technology. So it comes down to saying poor software cannot be used as an excuse to limit science. We need the right tool for the job. So I can't go and cut the grass in a field using a scissor. Yeah, this is the right tool. So when you make decisions, you have the optimal tool available to you. And if not, well, you're just going to left behind in the march of technology. So you need to be able to say, I'm doing the right tool for this job and the appropriate solution. So why has simulation been limited? Well, most sites, most plants will just have a single workstation. Over the last decades, you had CPU computing, which was the main thing. And there you needed a very large cluster and you needed a huge amount of power to solve these things. When you had simulations, you could only do a very, very small scale. So you could do, here's a mill, here's a full-size mill that we want to do, and here is what we actually get, a digital twin. That's not a digital twin that's going to be useful. So that is a huge challenge. And when we do get something that's slightly larger scale, you wait months on end to get an answer. And in a environment where you want to answer things in a feasible time, it's not sufficient. The second challenge, again, is particle shape. So you have various different estimations of these. And the most expensive here is the polyhedra. However, they're the most accurate. And here we look at the Mars rover, and everyone knows the Mars rover got stuck because the track got punctured. And that's because when they did the simulation, they assumed that the rocks were smooth, with spheres or clump spheres. So particle shape is very, very important. And in an environment where all we deal with is rocks, we should really consider this. So it's not all doom and gloom. GPU computing is enabling the fourth industrial revolution. So industrially relevant sizes of equipment can be simulated. You can use it for getting various automation, and it can be used as a tool to support the typical operation of a mine. So GPU computing is a tool that we are using here. And when you have the optimal software, what does it mean for us? Well, here we look at a solution. We look at a solution running on CPU using one software called Lights and the software that I developed called Blaze. And essentially, it takes you from going to do a single slice of a mill. It's like I'm watching television with a black and white TV with this box. Everybody should be familiar with that television. And suddenly, you go to a Ultra HD. So in the same amount of time, if you have the correct simulation software and the tools, you can do simulations of your entire devices or processes and make that a reality. So quickly, what are the physics fundamentals that you need to understand? Well, comminution, well, the aim is simple. We want to reduce the size of the ore extracted from the earth via mechanical means until the desired mineral can be efficiently liberated. So, and where we go on to flotation or chemical or other leaching things. But the fundamental one is we keep going to be reducing the size of this. And the physics is also simple. The material that we have, rocks, are crystalline in nature. It induces brittle fracture. Once we get to a certain size, the momentum of impacts, we cannot go beyond a further. We know this very, very well. If you can see the graph on the left, we understand this. So it's a typical Weibull distribution. And we know for a given size what energy we need to deliver to the particles. And this is something that various other industries don't have. But the challenge here is here, I've taken, they're exactly identical. We've dropped them. And depending on the angle they've impacted, they've fractured in different places. Different pieces, different sizes, different shapes. And what that tells us is just saying size and energy is very, very, very poor physics. What we need to consider is the shape and how that goes on. So while we think we have everything, the actual physics that goes on is far more complex, and you need to account for this. So the challenge is, how do we create the optimal conditions for breakage inside devices? And without particle level information, it's impossible to obtain. So when we use this tool, this technique called DEM, we get particle level information that we can use. So what is DEM? Well, it's simply each rock, each particle, each ball in your mill, in your chute, in your crusher, in your conveyor is explicitly simulated on the computer. One of the challenges, so if somebody wants to know technically, I'm not going to spend too much time on this, is there are various computational techniques that you can use to solve this problem. However, for most people in the audience, you are going to get software that already does this. The key thing to look out is when you get software, you need to ask them, what type of problems is your software optimal at solving? Do you say, I need all of my particles to be the same size? Can I have them dispersed? Can I do an entire line? So this slide, don't worry about too much technically, but look at it as saying, when you get software, you want to know what's inside it, because you want to know, can it solve my problem in a sufficient time? So to reproduce this physics, we've developed contact models that allow us to account for the shape and for the various size of this, and we've tested it against experiment. We've looked at the crack propagation. We've looked at here, we've then tested it further to say, can we get thermal transfer correct if we need to add additional physics? Can we look at cohesion? When we have slurry, how does it affect things? So in order to get to this point of this virtual plant, you have to create tools, software, and to answer that. So I'm now going to move on to what I hope everybody's still awake and they're still interested. We're going to look at a typical ball mill. And here we've done a full length simulation of this ball mill. Ball mills are the most suited to DEM simulations because you have spheres as your particles. And in general, you can get away with even doing a slice because apart from the axial discrepancies that you get where with your pop lifters, it's fairly symmetric. So a full simulation will take you about 3 hours of a ball mill doing a 1-to-1 DEM, while a slice will take you about half an hour, probably less. You can use this then to train AI models to give you something, and you'll see as we look in towards the end where we look at an example that will be real time, or we can use it for offline studies or semi-real time as a pure DEM simulation. And we know we've had these for a while, and what would be a typical analysis you would do? Well, DEM simulations for the last 20 years have been used to give you information like this. You look at the charge profile, you look at the throw, and you get the power. Cool. You change the lift angle, again, charge profile, and the throw. You can see as we change this, the throw gets closer and closer into the belly, more expanded charge. Power changes a little bit, but we can design the optimal throw. We can also get this information from the plant. Well, not the profile, but the power. And power itself is not very useful because it doesn't tell me what is going on. Yes, I can see how the charge is moving, but what I want to know is the fundamental thing of comminution here, breakage. And when I look at this, now we look at a little bit more in-depth analysis. So here are the different designs, different lifter angles. And here we've broken up the power between what goes between the particles impacting, the particle shearing, impact with the mill, so with the liner, and shear with the liner. And now we can evaluate these designs by saying, okay, what do we want? We want to decrease wear. We don't want to wear our liner out. So what we've done here is we can say, okay, we take the designs that at least reduce wear, but we also want to have more shear. We don't have too much of shear because then we're going to start introducing slag in the mill. It's going to become problematic. So here we can do some in-depth analysis just based on the information from a DEM simulation. We can go further into this. Now that we can do this on GPU very, very fast, we get an in-depth analysis. We can look at particle level detail, and this is the energy spectra. We can optimize, look, where are the grinding zones happening? What's going on in this? And we can do that just from the simulation data. Now it's starting to get a bit more useful. Here we can go even further. Okay, here I look at the shear event. So in a ball mill, I care about shear. We'll see later on the sag mill, we care about impact. So what we do here is we look at, again, these different angles, and we can look at saying, I want to have, do I want more high energy impact events? Do I want low energy events? So something, again, very useful. We can look further at this to say, how does this affect? And here we're saying, if I have spheres and I have actual rocks, polyhedra, so in a different mill, how does it affect things? Here we look on the left. So if I've done a simulation of a ag mill or sag mill with spheres, it gives me this answer. And if I take into account the actual rock shape using polyhedra, I get this answer. And this starts telling us now, actually, this particle shape is very, very important. You can look at the energy, the impacts, and the shear is very, very different between the two. The second example that we can look at here is stirred mill. So if you want to do ultrafine grinding, and here you will notice that we have some cubic particles. And what we noticed in these mills, due to the compression, the balls actually deform and they're no longer spheres. So with the simulation, we are able to track the motion of balls. We can look at the optimal grinding. We can look at the optimal impact energy. You can then see for this, how much of power is useful. And here we look at the total power and you can see, so PP is particle and PS is particle surface. A lot of our energy goes towards here, shear with the shaft. So I might be drawing a lot of power, but am I doing anything useful? No. And this is where physics-based simulations come into their own, because they tell you how much of your desired output you're getting from this. You can then go ask design extreme questions. What if I tilt the shaft? What's going to happen? I can't do it in a real life example because I'm going to break things. And here we can see so we have a tilted one. We can look at, we have much higher wear. Okay, it's vertical, the wear is reduced. We can look at what's the impact, what's the energy being dissipated. We can ask question on extreme designs. Okay, if I make it completely horizontal, what happens? Okay, I reduce the wear on the shaft, but I get less breakage. And this is where a virtual tool, a digital tool, is very, very useful. I'm going to now go on to the final thing that we're looking at, is a sag mill. So here is where particle shape is very, very important. For a number of years, people have been using spherical particles, saying, okay, it's a lower fidelity model, but it's sufficient. Well, we'll show here that while you can tune spheres to give you the correct answer, it's not true. And the second one is you want to understand your entire device. And what we show here is that the larger particles, if you just did a slice of this, you are missing information here, your larger particles move to the end of the mill. That causes more damage on your power lifters. This is something that's very important. It's something that's been ignored for a number of years. So, and again, what are the effects of this domain size? So when we want the correct tools, we must need to make sure that they're appropriate size. So a number of others listed, so for Mark Sherman, who's an expert in this, and various other authors have said there is an effect here as you go in a sag mill that needs to be considered. Larger particles, and we showed you it's the larger particles that migrate to the end and cause impact with the power lifters that causes damage on them, and then that reduces the overall lifespan. So this shows us that we need to make sure we look at the entire picture when making decisions. And again, we looked at shape here. If I do spheres, if I do polyhedra, different types of polyhedra, you look on the right, we are able to show that we get a very, very different behavior in the mill. So finally, we come here to say, okay, what does this mean? Spheres, scan polyhedra, actual rock shapes, and approximate polyhedra. And we can see that there's a big difference in the power draw. So the spherical particles significantly underpredict power. So if you are using information from simulations coming from spheres, you need to be aware of this. And now we look at the way. Well, no pun intended. But you can see if I use spheres, I get completely different behavior. That means I'm not going to estimate the lifespan of these devices correctly. And the question is, does it affect breakage? And here we look at this, and we can see a difference in the energy spectra. The energy spectra, it tells me when I have collisions, what happens? And we can see it's fundamentally different. So this is, hopefully from this, it shows us that we cannot just say, we have a physics simulation, let's go with something that's fastest because my software can't do this. We need to ask questions of what's important to us. And here, as we move towards these things, we show that particle shape is very, very important. It's something that you should consider. And as we move towards this is when you have something that runs so fast on GPU, this is a VR simulation. So I've put the entire simulation in VR. You can now go and explore the wear happening in your mill. You can change, you can look at the material, you can see what's going on. Now we've pulled out the rocks. We're looking at the rocks, we can look at the balls, and it's endless the possibility that you can do this. And this is taking us towards that vision of having all of this virtually. And a mill digital twin. So one of our partners, ECN Automation, they have used the software that I've showed you now, the last bit, as an engine in their digital mill tool. And you can have a look at their website to see how this can be used for mill operation. It's really, really cool tool. And it uses the proper fundamental physics as you've seen in the solver. It combines a variety of data coming from your operation together with simulation, in cases where simulation would be too slow, to supplement that and give you a complete solution. This is other work that we've done with a colleague of mine, where we're doing virtual sensing and farm telemetry. If you give the power draw, having trained a AI-based model using the DEM simulation, we can predict the charge profile and what the behavior is going to be. So this is taking us to say, from this detailed DEM simulation that now runs very fast, I can put higher order models that allow me to have this environment where we can do semi-real-time information. And this is a video of the ECN's automation tool using the BlazeDEM solver, where you can see a variety of information, operating information, and what's going on. It's automated calibration, automated reports. So all of the physics that I've showed you, all of that, you don't need to worry about. You will just input your information here on your mill, your RPM, your charge, your shape of your ore, and it'll calculate it for you. So what I hope to have done here was, as I move on to the summary, was give you an overview of the current models. What are their limitations? Because we cannot base our thinking of saying, okay, this has worked for the last 30 years. We have to use new science and new technology to advance and become more optimal. We looked at the role that DEM simulations can play in moving to digital twins, some limitations of CPU software being very slow. We looked at, even when we have a simulation, I need to make sure that right things are in that simulation. I need to make sure I consider my particle shape. I need to ensure I have the full domain, that I'm answering the right questions. And finally, an outlook towards cloud-based simulations automation using a GPU non-store-based tool. So I hope the fundamentals, if you remember nothing else from here, use and look for software where the physics is apparent and you know what you are simulating to get the best answer going forward. Thank you, Dimitri, for inviting me again to talk at the conference, the organizer of APC. And if you have any questions, please contact me. Thank you.